Hey guys, good morning. Um, it's been a little while. I apologize. I wasn't able to post this video on Friday as I had intended. Um, and it feels like a lot has happened since then. Um, I had a little department going away, an outdoor kind of get together. Some friends of ours had a baby. My wife was up all night helping them with that. Um, we started trying to find a house in Albuquerque, um, and with travel the way it is, we've been trying to do it digitally or like via FaceTime. So we've been looking at houses a lot and making appointments with a realtor when she's there to kind of walk through them and do like this virtual walkthrough, which I don't know about you guys, but I'm kind of getting tired of this whole virtual everything or digital everything. But I made it hard to sit down and record a video only one shot because it was like spread out throughout the day. And if I'm honest, I'm ready for this quarter to be over. You guys may feel the same way, ready for things to get progressively back to normal. And with me, well, I won't be in normal for a while since I've got this big transition coming. But all that aside, I'm sitting down. We're going to talk about etching, and I'm also going to try to catch up at some point this week. But we're going to kind of play this rest of this quarter by ear. I still owe you graded homeworks, and we may be pushing back the due date of homework 6, but that's TBD. At any rate, let's get this discussion of etching done. So I'm going to go ahead and switch over to the notes so we can talk about this. All right. So far, right, we started talking about crystals, then we talked about oxidation, ion implantation, rapid thermal processing, then photolithography, then plasmas and vacuums. Now we're talking about etching. So after we make the single crystal and we dope it and we pattern it, right, after the photolithography, we're left with a pattern of photoresist, right? So we have chemically changed the photoresist in the regions where we exposed it. That either made it more or less soluble to the developer. So now we have regions where we have small regions where the photoresist is remaining, and nearby we would have silicon or silicon dioxide that is not covered by photoresist. And the etch step is where we take that pattern that is represented in the photoresist and we make it permanent in the underlying material, whether that's silicon dioxide or silicon or what have you. Then the photoresist can be removed, and the pattern will be there in the actual silicon. And that's done by etching. And when we are etching, right, we care about a couple of things. The first is the etch rate, right? So all of these processes are part of a larger production process, and the economics of that process favor performing them relatively quickly, right? Because if you need to maintain a vacuum or a flow of expensive chemicals or just need to buy the equipment in the first place, right, you want to be able to have relatively high throughput, and for each to have high throughput, right, you need each step, or each individual product piece, right, needs to be completed relatively quickly, right? So you want it to be a high etch rate, meaning you're going to remove material quickly, in the region of tens to hundreds of nanometers per minute. But you don't want it to be so high that it's uncontrollable, right? You wouldn't want to etch all the way through a layer, say, that you want to remove a lot faster or slower than you had anticipated, and then either not remove it completely or start to remove other areas that you hadn't planned on, right, or etch too deeply, that sort of thing. You also want it to be uniform, right? Remember, we have large wafers with many devices on them, and you want the device that is made near the center of the wafer to be the same as the device made near to the edge of the wafer. So the etch rate needs to be uniform over the whole surface so that you get the same product from the center out to the edge. The second is you care about the selectivity. So, and this will vary depending upon what etch process you're talking about, and we actually kind of have a spectrum that we'll talk about a little bit later. And one way that those different processes really differ is in selectivity, meaning does the process etch one material a lot faster than another material, right? And if you have a process with high selectivity, then you can actually use that to your advantage and say etch away one type of material that is in one region before you remove another, right? So for instance, in this picture, the oxide had a much higher etch rate than the photoresist, right? And so we exposed the whole surface of this wafer to whatever the etchant was, the etch process, and it attacked the photoresist very slowly, so that's mostly intact. But the oxide was etched away much more rapidly, and so not only is the oxide gone, but it actually starts to undercut the photoresist a little bit. And so you see selectivity in silicon versus photoresist, also in silicon versus silicon dioxide. This would allow you to remove an oxide layer and then essentially stop once the oxide layer is totally removed. And you reach the silicon if the process is highly selective for silicon dioxide. The third thing, which I kind of talked about just now, is undercutting. So if you have, and this is also one of the ways that we differentiate our processes from each other, is in the anisotropy. So if you have a process that etches basically uniformly in any direction, then once you get down into the material, say this oxide, we're moving down into the oxide, right? There's really nothing preventing the etchant from etching laterally under the photoresist as it continues to go further down and remove the oxide layer. And so if you have an anisotropy of 0, perhaps, then it's isotropic and it's going to etch in any direction. It doesn't really matter. There's no directionality. And so we have this value here for the anisotropy of the etch. So this is A minus 1 minus the etch rate in both the lateral and the vertical direction, right? So if there's no difference, then this is 1 and this A value is 0. If you have a much higher etch rate in the vertical direction, meaning downward, right, removing the material and leaving a nice sharp edge here at the edge of the photoresist, right, then this quantity R sub L over R sub V would be very low, which would give you a rather value for A that's pretty close to 1, which would indicate a high anisotropy for your process, right? And this is one of the ways we differentiate our processes relative to one another. And it seems that you have kind of a trade-off in selectivity versus undercutting. So if you have a very selective, well, I should say selectivity and anisotropy tend to be opposite, right? So if you're going to have a very selective process, then it's probably going to be rather isotropic because the chemical doesn't really care if another atom or molecule is directly below it or directly to the side, right? Because at that scale, gravity is not a factor, and this may not even be, held upright, where this photoresist is pointed upward and gravity is pulling it down. Anyway, okay, so so those are the big three. You also care about sample damage, right? You don't want to be leaving imperfections at the end of your process, and the hazard level of the process is also a consideration because you need people to be around and working in these areas. And so that is a hazard, but can be managed. But managing hazardous chemicals comes with risk and cost. And so if you can avoid it, that would be preferable. And so I kind of drew this picture here. We kind of have, like I've mentioned a few times here, the spectrum. And on one end of the spectrum, you have wet chemical etches, and these tend to be um, very selective, right? So it's purely a chemical process, and so the chemistry involved in will make it selective for one material versus another, meaning that the chemistry involved in removing an oxide is different than removing the silicon, right? Because the bonds between the silicon and the oxygen in the oxide are much different than the silicon to the silicon in the silicon substrate underneath the oxide. And so, and the bonds in the photoresist are different than the oxide as well. And so, the more chemical nature you have, the more selective the process tends to be. And it will be selective and non-damaging to other types of materials, right? So a chemical etch designed for oxide is not really going to damage the silicon once the oxide is gone. On the other end, we have ion milling, right? And this is the opposite. I'm just going to introduce it here, right? So an ion milling tends to be very non-selective, right? You have ions that are impacting on the surface, and they're going to eject whatever atoms they impact. And so it doesn't really matter what atom that is, but the ions are also moving in a particular direction, right? So if we are ion milling, say, this area instead of etching it with the chemical etch, right, the ions are going to come straight down, and they're going to eject all of these atoms, right? But if I don't stop ion milling after the oxide is gone, then I'm going to start ejecting the silicon, right? And I'm also not going to undercut because the atoms have a trajectory that's straight down. So on the one end, we have selectivity, but no anisotropy. On the other hand, we have no selectivity, but very high anisotropy. And then there's a few processes in between that kind of give you a mix, right, where you have some chemical and some mechanical processes going on. Okay, so that's the spectrum. We have the wet etch, so it's selective, which is good. It's non-damaging, which is good. But it can be difficult to control because the chemistry is not, chemistry is not like a switch. You can't as easily just turn it on and off like you could with, say, an ion gun. And also, you have contact. So if you recall in, contact masks in lithography, anytime you have contact between two materials, you have the opportunity for defects to form, whether there's particles remaining on the surface or pits or something like that. Also, chemical processes, which is what wet etch processes are, lead to chemical waste, right? So there's a hazard there, there's a disposal problem there, and the etchants can be particularly hazardous, right? Hydrofluoric acid is really corrosive and hazardous to people, and also no anisotropy, as I mentioned, right? It's going to undercut to a high degree. It's not going to be selective for any direction. Okay, and so yes, it's a chemical process. Wet etch is a chemical process. So anytime you have chemistry, you have a kind of a similar set of issues. You have to worry about diffusion. So the reactants need to diffuse to the surface, say through some boundary layer or out of some flow, and then you need to diffuse the products away from there. And so chemical processes have multiple steps, right, where you have diffusion through various layers, you have reactions, maybe you have intermediate reactions, and the slowest step there will be rate determining. You also have, like I said, diffusion through various layers, and you have regions that are being depleted by the reaction, and so on and so forth. And so, as a chemical process, right, it's consuming chemicals, it's producing products, and so you need to keep it mixed to do that, which presents a challenge to maintaining a uniform etch rate, right? Because you have a dynamic situation. Sometimes the products that form as a gas, and so that gives you a gas that forms on the surface, and that forms a barrier, right? If you have a bubble there, right, that slows the etch because now the other etch chemicals cannot get to the surface, And that could form a defect, right, where that bubble is, because now you're not etching away that material that you should be. And chemical processes are dependent upon cleanliness. So if you have residue on the surface, say from photoresist that was not completely removed by the developer, right, then you may have, say, a thin layer of photoresist, but if your material is highly selective and not very doesn't aggressively remove the photoresist, then even a thin layer can protect the surface and you won't be etching areas that you had intended to etch. So a common chemistry here, as I mentioned, is removing oxide with dilute hydrofluoric acid. Hydrofluoric acid is really nasty stuff, so there's a chemical hazard for sure there. And HF is very selective for oxides, even for all oxides, but even more so for deposited oxides, right? So these would be ones that were deposited through a chemical vapor deposition, say, which is a process we haven't talked about, but essentially it would be a chemical reaction that happens on the surface as opposed to oxidizing the silicon from the substrate. And so deposited oxides tend to be less dense, and so they etch faster. If the oxide was grown from doped silicon, that's going to increase the etchant rate. And the selectivity for HF is very high for the oxide over the silicon. We're talking greater than 100 to 1. Right, and so you're consuming HF via this reaction here, where you have the oxide plus a certain number, in this case, I guess 6 HF molecules. And so the silicon goes from being bonded to the oxygen to being surrounded by fluorine atoms, which we'll talk a little bit on the next page about the mechanism. And so this takes it from the surface, right, into solution to be removed. And so removing silicon, because HF is very much more reactive to the oxide, if you need to remove silicon, there's an intermediate step where it needs to be oxidized first, then it can be removed much more easily. If you recall back to 680, for those of you who are in that course, when you do metallography, that is, you're examining metal microstructure, after you grind and polish, right, you get it to a mirror surface, and then to see the grain boundaries, typically there's an etchant. And the etchants are tailored to a particular alloy. And so the etch chemistry is the same thing here, where the etch chemistry is different for different substrate materials, right? So if I'm etching silicon, I need different chemistry, different chemicals than if I'm etching, say, a compound semiconductor like gallium arsenide or gallium nitride. Here is a common etchant. So we have a mixture of HF, nitric, so hydrofluoric acid, nitric acid, and then acetic acid. So there's sort of this acid cocktail that is used, and the etch rate can be tailored by mixing the proportions of those various acids. And so you have these contours here in this kind of triangular plot that has the percentage of the three components here, and you can see that the etch rate varies quite a bit, say from less than 10 to about 100, depending upon the proportion of these etchants, right? So as we increase the percent of hydrofluoric acid, let's see here, the contour. So the contour here is shown in the etch rate. So this contour is 482 microns per minute. Down to here it's 7.6 microns per minute. So you can see here it's not as simple as just saying you need a lot of one thing or another. There's an interplay between the components. So right, if I want a really high etch rate, if I have, say, 50% nitric, 50% hydrofluoric, right, that's going to be pretty high, and then it would be 0% acetic. But as I add in more of the acetic acid, then I'm going to intersect here at these lower etch rates. At any rate, yes, and also the etchants are selective with respect to crystal direction, which should intuitively make sense when you're talking about breaking bonds, right? The strength, the distance between atoms, the strength of the bond differs depending what crystal direction you're talking about. Okay, and different etchants also can select for doped regions, which, if you look at, if you know well the etch rate as a function, say, of defect or doping level, then you can actually use that to characterize your device. Okay, so that's chemical etching. A related process, which is not, I mean, this is not really chemical etching, but it's used in the same vein. It's removing surface material, is chemical mechanical polishing. So here again is a form of kind of hybrid between chemical action and mechanical action. Here, the mechanical plays a dominant role in that we are polishing. So we have abrasion, we have a medium that is lubricating, and particles that are abrading away the material. And this is used to produce globally flat surfaces. So like you might expect, right, with polishing, you're just trying to get it to a really flat surface. And so this step would be necessary when you're making really small features, because remember, when we're making small features, one of the tricks we use to achieve that higher resolution is by reducing the numeric aperture of our projection system. So you have a small numeric aperture or a high numeric aperture. That means you're going to have a small field of view, and if you have a small field of view, then you need your surface to be flat so that you can have the whole surface in focus at the same time. A lot of these processes, especially like lithography, is aided by having a planar surface, and so this is one way that you can use to achieve that planar surface is by polishing. So during this process, right, you have chemicals, particles, and pressure. So your slurry is going to have chemicals to lubricate, and then particles to abrade, and then putting pressure on the surface, right, brings the particles on the surface like into contact, and leads to that polishing action. Here you're going to be removing hundreds of nanometers per minute, so not too fast, but a good removal rate. And your slurry is oftentimes water-based, so what's actually happening is you're hydrating the surface and then abrading away that hydrated surface. So you can, right, remember, silicon will oxidize at room temperature in air. When you have this water layer, you're also going to be oxidizing that. So, and we saw that in the case of chemical etching, it was really a lot easier to remove the oxide than it was to remove the silicon. So you have this continual process where you're sort of forming a hydrated surface layer, and then removing those hydrated atoms, and then continuing that process. The more pressure, just like any other sanding or polishing operation, right, the more pressure, the faster you're going to remove the material. And you want to pick your particles to be softer than your wafer, right, because that leads to a slower abrasion. You're going to be, just like any sort of polishing operation, is that you're going to the softer your particles, the gentler the action, the slower it is. So there's a balance there. And so you have this, you have a slurry with your particles. You also have this polishing pad, which is consumed over time and has to be reconditioned or replaced. And then, of course, you want to clean up the wafer to remove any particles or chemicals before going to the next step. So on the one extreme, we have wet etch. And they haven't talked about it yet, but on the other extreme, we have ion milling. And then in the middle, we have processes that take advantage of the plasmas that we talked about in the last lecture. And so one step away from wet etch is plasma etching. And this has the advantage of the plasma being turned on and off. So you can start and stop the process at the flick of a button, as opposed to the chemistry, which is not controlled via a switch, and you have to remove the chemicals to cease the reaction. It is also less sensitive to wafer temperature. So I didn't mention this, but with the chemical etch, you want to have a uniform etching across the surface. But remember, anytime you have a chemical process, right? Every time we've talked about chemistry, we've said, okay, many of them are Arrhenius processes, which are exponentially dependent upon temperature. So the rate of the reaction increases very rapidly with temperature, and so if you have a temperature variation, then a wet chemical etch is going to have a change in etch rate. So chemical uniformity or temperature uniformity would be very important to achieving uniform etching. With plasma etching, it's not as sensitive to that for reasons which we'll talk about here. And because you have a plasma, remember, a plasma is made of ionized, partially ionized atoms, so you have ions which you can then accelerate in a particular direction, right? So if I have atoms moving in a particular direction, that gives me anisotropy, right? Meaning they're going to remove material in one direction preferentially over another one. And since I'm not relying totally on chemistry, I have less surface contamination and less chemical waste. Okay. So to have a plasma etching, obviously you need a plasma, and so you have a feed gas that is that has your chemicals that contain the atoms that you are using to etch with, and the reaction is cracked by the plasma. So you're injecting energy into the reaction using the plasma, which shifts. Sorry. If you hear the screaming, that's my children in the hallway outside. So your reactive species are created by the plasma. So you have a plasma, you're creating reactive species. There's still an element of chemistry because those species need to diffuse to the surface, then react, and then be desorbed and diffused away. So you still have that chemistry going on. I think she's going to be okay. It sounds worse than it is when you're 3. Okay, so in plasma etching, and you can increase the rate by increasing the pressure, so you have a higher pressure of your reactants in the plasma. And here we have some of what I said about shifting the reaction energies using the plasma. So Campbell gives you some numbers. I don't have it reproduced here, but essentially, if I'm going to use a fluorinated carbon molecule, right? So I have CF bonds, and I want to etch away silicon. In order to do so, I need to break both the CF bond and the silicon bond, and then reform the silicon fluoride bond. Now, this is a thermodynamically, favored direction in the sense that it's exothermic. I'm ending up in a lower energy bond than I started in. However, I need to put in a little bit of energy, right? I need to put in more than I get out momentarily to break these bonds, right? I end up in a lower energy state at the end, but I have a higher energy intermediate, which means that this reaction all by itself has an energy barrier to get over before I have reactive species that can then end up in a lower energy. And so what the plasma plasma ions do is they provide that energy to break up these bonds and create these reactive species, which can then form this lower energy bond. So it's kind of like priming the pump or seeding the reaction a little bit by adding these plasma, these ions that can create these free radicals um, through collisions. And so that takes an endothermic reaction and suddenly makes it exothermic, which greatly increases the rate. And so we're going to care about, since we have these collisions driving the reaction, we care about the flux, right? So if we have a higher flux, we're going to have a higher etch rate. And here, since this is, remember I said, on the one hand we have chemical etch, on the other hand we have ion milling, this is somewhere in the middle, we have a combination of chemistry, which is the free radicals that are attacking the surface, and physical action, because we have these ions that are colliding with these free radicals, and maybe to some extent also the surface. And so there's this combination of chemical and physical attack. And so we have some sort of mechanism, like something like this, where we would have a free radical fluorine, which would bond to the surface to a silicon. And as more fluorine atoms bond to the silicon, what it's doing, remember fluorine is very electronegative, so it's going to be pulling electron density away from the silicon. Maybe I can zoom in. It's pulling electron density away from the silicon, which weakens the bonds that it has to its neighboring silicon atoms. And so the more fluorine that bonds to that surface silicon atom, right, the less strong these bonds are to the silicon atom of the surface. And so eventually it has so many bonded to it that that it breaks that silicon bond totally, and you form this silicon tetrafluoride atom that can then diffuse away from the surface, and you have removed some of the surface silicon, i.e. you have etched it away. And you can tailor the selectivity of this reaction by the composition of your feed gas, right? So if I want to remove silicon over the oxide, then I can add a little bit of oxygen to the feed. If I want to remove the oxide over the silicon, right, I can tailor that by increasing the hydrogen in the feed, which I guess if I go back to this reaction here, well, that's a wet chemical etch. I don't have the reaction here for that, but anytime that you add one or another, you push the reaction, right? I think this is called Le Chatelier's principle, but you push the reaction one way or another, right? So adding more HF is going to push the reaction this way, adding more hydrogen would push the reaction this way. Of course, we're talking about plasma etching, so you have that additional plasma action as well. But all that to say is that if you have a chemistry element, right, adding more reactants or more products can push the reaction in one direction or another. We can make use of that by tailoring the selectivity of this plasma etching process. This is not highly anisotropic because the etching mechanism is fundamentally chemical, right? You're just using the plasma to create these reactive species, and then they bond to the surface, and they don't really have a directionality because they could bond to a silicon on the wall or on the floor of some etched region, and so the anisotropy is not huge. However, you can make it more so by adding in fluorocarbons, and so what happens is the fluorocarbons coat the surfaces of the walls, and the small degree of ion bombardment. So we have plasmas that are formed, and then those ions can be accelerated towards the surface, right? I have a largely chemical reaction, but I'm going to increase the flux of those reactive species parallel to the surface, and if I have a protective molecule that film, that protective film, will be there on the walls and not be removed in the same way that it would be removed by this ion bombardment on the floor. So using that mechanism, I can make this process more anisotropic than it normally would be. This process, there's a lot going on here, right? You have your plasma generation, you have ion bombardment, you have chemistry, and so it's not as easy to just say, model using your input parameters how much etch rate you're going to get and how long you need to run the process for to get, to remove however much material that you're trying to remove. And so generally you're going to monitor the film thickness. And we talked about this a little bit with the oxide, in the oxide chapter of monitoring film thickness. And we talked about optical interference type measurements. You can also monitor the exhaust gas. So if your exhaust has a certain proportion of products, right, then you can deduce your etch rate, and that might be more accurate enough for you to run your process. Just jump ahead here. Okay, about halfway. So I think I need to speed up. All right, so on the other end of the spectrum, we have ion milling. And so this is a purely mechanical process, right? We don't have chemistry involved. We're just bombarding the surface with ions and removing some of the material. So this is really similar to SIMS that we talked about in material 680, secondary ion mass spectrometry, where we're removing ions with ions. And we had dynamic and static SIMS. Dynamic was actually sputtering away material. That's essentially what we're doing here on purpose, right? We don't really care what is coming off. We're just trying to remove the surface. And so it's not selective at all, right? Like the ions are going to hit what they hit, and they're going to remove it. And it doesn't matter what they hit. There's little selectivity. But what you get is high directionality, right? So there's this trade-off between selectivity and anisotropy. So if it's not selective, then it's going to be anisotropic. And so this gives you the ability to etch deep, high aspect ratio features in the way that you couldn't with more chemical processes because of that undercutting. However, you can't just stack up wafers and flood the whole, and then flow chemical reactants around it and etch many wafers at the same time. You need to do them one at a time because they need to have exposure to the ion, right? So this is lower throughput. And you generate the ions similarly to the way the ion gun worked with SIMS, where you have a filament that's blowing off electrons. Those electrons are being accelerated. And you flow a feed gas through here, say of argon. That's a good etch gas because you've got a relatively large atom that's not going to react with each other because it's a noble gas. So the electrons collide with the argon atoms. They form argon ions, which then you can then accelerate. That becomes your ion gun, your ion source. However, the ion milling can have some problems, some complications, right? The first is that you are going to be basically etching uniformly over everything. So if I have a taper in my photoresist, right, with this region where it's tapered, I'm going to etch through this part here where it's thinner before I etch through this thicker part, which means that eventually, before I etch away this layer, I'm going to start etching away the substrate below it. So I'm going to reproduce this taper in my substrate if it exists in my photoresist. I also could have redeposition. So if I'm coming and I'm removing this material, not all of it is going to just be swept away or ejected straight outward. I'm going to have some that gets redeposited, say, on areas nearby. I also have, sort of ricochet or deflection of these ions. They're going in all directions, and some of the time, I could be reflecting or deflecting the ions straight downward, in which case they're going to be funneled into the region that's directly beside this high aspect ratio of this photoresist, and I might be milling a trench. And so there are unintended consequences of using ions relative to the chemistry. So you get the anisotropy, you lose the selectivity, but you can come with some of these problems. So not every process is perfect. So another process that's sort of somewhere in between is this reactive ion etching. So in the plasma, the high density plasma that we talked about a few pages ago, you're using the plasma to create reactive species. Here is a little bit more chemistry. So you have a chemical process as well as the ions. And so you could have a process gas. You would have the participation of halogens, especially chlorine. So you form the negative ions in the plasma, and those ions bond strongly to the surface. And so the reaction, the chemical reaction is between the chlorine and the silicon, but you put the wafer on the electrode, and the bombardment increases the penetration of these chlorine atoms into the surface. So under purely chemical conditions, you would have this layer of adsorbed chlorine, but what you need to do is to kind of get in there and get multiple chlorines to weaken these bonds, remove these atoms, similar to the mechanism we talked about with hydrofluoric acid attack. Right, these chlorine atoms are not quite as electronegative as fluorine, and so you can help the reaction to go forward by impacting these chlorine into the surface and kind of mixing things up a little bit to help it increase that penetration. But so somewhere in between where you have this chemical reaction, you're helping it mechanically. You can also have erosion of the photoresist, and so depending on what etch process you use and how you run it, right, it gives a degree of tailorability that you can use to achieve the desired end result. But you have pros and cons, just like in anything. So the more you have ions, the more you can have residual damage, right? You're using that penetration to increase the reaction, but that penetration itself can be making damage in the surface. And sometimes when you have these hybrid processes, you can actually get, cons from both ends of the spectrum. So you can have residual damage from ions. You can also have chemical contamination due to the etching, where you would have, say, leftover passivated films, or maybe the ions would be sputtering metal surfaces somewhere else in the chamber, creating impurities, in which case, and you would also be driving those impurities deeper into the material. So there's no free lunch, just like anything else. Anytime you're using a plasma, you can increase the rate further by just increasing the density of the plasma. And when we talked about plasmas in the last lecture, we said, okay, you can use magnetic fields to basically swirl the electrons inside the region where the plasma is forming, which increases the probability that they will have that collision and increases the ion density and gives you a denser plasma. So for denser plasmas, you don't need as high a voltage. You can reduce. So if you have more ions and each of them are going slower, then you can get a higher rate with less surface damage. All right, so that covers kind of our spectrum. The last topic is liftoff, which is a bit of a different but related process. And so there's lots of different etch chemistries, but some materials are just tougher and they're harder to etch. And so those surfaces can be patterned by a different material, a different process called liftoff. So in liftoff, what you do is you use the photoresist as your pattern, which is normal. So you do your photolithography, you develop your resist, so you have exposed and unexposed, and then you'd have areas where, oh, that's right, sorry. You expose the photoresist, right, so that you have regions that have been toughened or softened, right, but you don't yet develop it, right? So I still have a solid layer of photoresist, but some regions have been exposed, and so they will be removed or not removed later on when we develop. But before we develop, we apply a thin layer of metal. So that metal is going to cover everything. Then if I do the developer, then I'm going to be removing the photoresist that I would normally have removed, except it's got metal on top of it. If I remove this photoresist, then the metal will be removed also. And I can use that to create a pattern here, where later on I can then evaporate metal again, and that that physical vapor deposition, which we'll talk about, is the process we use to deposit this metal. And then I'll have metal that bonds directly to the substrate and other metal that bonds to these regions of photoresist, which then when I remove the photoresist, right, I'm left with a metallized pattern here. So it allows me to create a pattern on a material that I can't etch away very easily, and so I can use the photoresist. And actually, this is a good example of using a disadvantage to your advantage, in that sometimes deposited metals have really poor step coverage, meaning they don't deal very well with these high aspect ratio features, which we'll talk about when we talk about physical vapor deposition. But in liftoff, you actually take advantage of that because you want there to be a break in the metal between this step. Anyway, okay, so I'm at time. That is etching. You have this spectrum between chemical etch at one extreme and ion milling at the other extreme, and then you have a couple processes in between that make use of plasmas and chemistry at the same time. But the goal is to remove material in the pattern that you established with your photolithography so that it is then permanent. All right, thanks guys. See if I can get another video here soon and get us caught up, but we'll see.